Okay. Good afternoon, everybody. We are here in our 42 section of our Applied Mathematics EDP seminar. And today we will have, in this afternoon, we will have two two people here. The first, it will be our Professor Cannarsa from the University of Roma, Tor Vergata, and Professor Cannarsa will be introduced by our colleague Diego Souza. And the second professor will be Damião Araújo Júnior from the Universidade Federal da Paraíba, and he will be introduced by Professor Mauro Rincon from UFRJ, Universidade Federal do Rio de Janeiro. It's so nice to have you here. And please, Diego,
okay,
the stage is yours.
Thank you. Okay, thank you very much, Sandra. So for me, it's a great pleasure to introduce Professor Piermarco Cannarsa from Università di Roma Tor Vergata. He's a well-known reference, mathematical reference in the world. He's a specialist in control theory and also in Hamilton-Jacob theory, and he has more than 3,000 citations in MathSciNet, almost 200 publications, and also he is involved in many administrative staffs. Nowadays, he's the president of UMI, which is Unión Matematica Italiana. And today, he's going to talk about Scalar-input bilinear control problems for evolution equation. So, Piermarco, thank you very much for accepting our invitation, and you can start when you want. Thank you.
Thank you, Diego, for the introduction, and thanks for this kind invitation. It's a pleasure for me to keep in touch with friends and with the mathematical world in Brazil, Spain, and so on, especially in these difficult times when traveling is a problem. Okay, so in control theory, we try to steer the evolution of a certain system by some kind of action. And in this talk, I will focus on a special kind of action, which is bilinear action. So what are bilinear control systems, scalar input bilinear control systems? Well, to give the idea, they are control systems which involve an evolution equation like this, where U evolves in, let's say, a Hilbert space, and the dynamics is represented by some accretive operator, an unbounded operator, which is the infinitesimal, such that minus A is the infinitesimal generator of a strongly continuous semigroup. And then you have another operator B, which we will assume to be linear, on which your control action operates. And your control action here is represented by a scalar function. Sorry, excuse me. Ma proprio adesso comincia qua congiunto. Okay, so to explain the difficulties of the problem, let us, for example, look at an application. Let us consider a stochastic process, a one-dimensional diffusion process, which is a solution of a, well, diffusion equation of this kind. Now W is a standard Wiener process, and the drift is represented by a product of a function of time and a function of space. Now, if we look at the probability density of the process, U, well, the function that represents the law of the process, essentially, it is known that this function U solves a certain parabolic equation, which is known as the Fokker-Planck equation. And it is this one. Now, when your process X is valued not in the whole real line, but in an interval 0, 1, for example, then you have to add boundary conditions, and you can consider different boundary conditions. Well, if you want your process to be confined inside the interval 0, 1, you can consider perfectly reflecting boundary conditions at points x equals 0 and x equals 1, but you can have also partial reflection, which means only the diffusive part of the process is reflected, and this involves Neumann boundary conditions, or you can have an absorbing boundary condition, which boils down to Dirichlet. So in this case, as you see, you have a parabolic equation, so an evolution equation for the density, on which you may hope to act through this P function, and you want to ask where can I take the density of the process by such kind of control action. Okay, now let us compare bilinear controls with additive controls. This is another important way to control systems. I act with an additive term and with some operator B. Usually, one understands that an additive control action is stronger than a bilinear control action. And for example, this is clear if, well, if you look at the output. In the additive case, the output can be expressed in closed form. You give P and you have the solution U, and so it's a linear affine response, and you can study this response by all sorts of duality techniques. In the bilinear control action, you don't have a closed form for the solution. The solution, the problem is nonlinear, is highly nonlinear, even though the dependence of, even if B is a linear operator, the control problem is nonlinear because here you have the product of the control times the space variable. And indeed, the solution can only be, well, characterized as a fixed point of a certain map, usual map. So, indeed, this weaker control action is reflected in an abstraction to exact controllability that goes back to celebrated pioneering work by Ball, Marsden, and Slamrod, who established back in the 80s that if you have a bilinear control system in an infinite dimensional Banach space, in fact, then the set of points that can be attained from a given initial condition by L1 controls has a dense complement. So it's very small. In fact, it's contained in a countable union of compact subsets. So why study bilinear control systems? Well, the thing is that in many situations, these are more realistic than additive controls. When you have like chemical reactions or systems which involve high energy levels, it is not realistic to believe, to think, to imagine that you can affect the system by an additive action, because you should be able to throw too much energy into the system. Or you should be able to reach each single particle. Whereas you may try to intervene by acting on the coefficients, even with a scalar function like this one, like this p function. Now, there is a fairly large literature on bilinear control problems, even in infinite dimension. But the ones, the papers that are mostly related with the model of this talk, the model of this talk is essentially a parabolic model, are, well, these papers by Karim Bochard and some of our co-authors like Camille Laurent, Morgan Morancet, and Frédéric Marbach. And especially the last paper by Bochard and Marbach, where they study bilinear control problems for one-dimensional heat equation. And in this talk, I will summarize results well, that have been obtained in a series of papers by Fatia Labo, Cristina Urbani, and myself, as far as controllability is concerned. We will see special kind of controllability, not exact controllability due to the result by Ball, Marsden, and Slemrod, but some kind of controllability to trajectories. And then I will also discuss another class of control problems where rather than controlling to a specific state or to a trajectory, you want to preserve some energy level. So these bilinear control problems are related to invariance results, and I will comment on this direction also. Okay, so let us start with controllability to specific trajectories, which I call eigensolutions. So to explain the setting, well, so we are in a Hilbert space, and we take an unbounded operator A, which is quasi-accretive in this sense. It is bounded below by a negative constant. Let's say self-adjoint, and let's assume that the domain is compactly embedded into the space X. Then, well, you can build an orthonormal basis in X, which consists of eigenvectors of A, and I will call such vectors by phi k. The corresponding eigenvalues, which form a monotone sequence, which diverges to plus infinity, will be called lambda k here. Okay, so the state equation, as we saw at the beginning, is an equation driven by A, like the operator we introduced above, and another linear operator P here, whereas our control function P is just an L2 function on some time interval 0t. And we will try to control the solutions locally, the solutions of this system, to solutions of the uncontrolled system, so with u equal to 0, but starting with the eigenfunctions phi k. So therefore, the solution of this uncontrolled system with initial condition phi k is just given by this evolution, phi k times the exponential of the corresponding eigenvalue. This will be called eigensolutions, and the first one, the one that corresponds to the first eigenfunction, is called the ground state solution. So in order to state the result, I have to introduce this notion, which is quite natural, and it refers to pairs A-B of operators. A, like before, accretive and self-adjoint, quasi-accretive and self-adjoint, and B, a linear operator. And we say that a pair, given T, capital T, and J, so this is referred to a given time and a given direction, J. The pair AB is J non-controllable in time T. If you can steer any initial condition, why not, for this system to 0 in time T by some control P. And you can do that somehow uniformly with respect to why not in bounded set. More precisely, if you can find a constant, n, such that for any initial condition, there exists a control P steering the solution to 0 in time T, and with energy of the control, L2 norm of the control, bounded by this constant pi y naught. If this happens, you can take the sort of the best such constant, which will be denoted by n sub j of T, by just taking the infimum over P and then the supremum on the initial condition. This is called the control cost. So this is just a definition. So AB is J non-controllable if you can control this system where J enters here in the, so this is a linear control system, in fact, no, because phi J is fixed, B phi J is given, so you try to, this is a really linear control problem. But you want to control to 0 with some uniformity. So with that definition in mind, we can state the main result here in this theory, controllability to eigensolutions. And it says that suppose you have a pair which is J null controllable in any time T, in any positive time. And suppose that the control cost is bounded, can be bounded in this way. It blows up as time tau goes to 0 on some, and tau is in some fixed interval, but at a sort of exponential rate, exponential of 1 over tau. So under this assumption, general controllability and estimate on the control cost, then your nonlinear system is locally controllable to the evolution of the J eigen function. More precisely, then for any T, capital T, you can find a neighborhood of phi J of radius R of T, sufficiently small, such that for any initial condition in such a neighborhood, you can find a control P steering the system to this eigensolution in time capital T. So this is the result, it's controllability to eigensolutions. Now, let me explain briefly the ideas that lead to such a result before going to extensions and related results. The idea is based on a sort of Newton type algorithm. By Newton type algorithm, I intend the following thing. Let's assume that J is equal to 1 and lambda 1 is equal to 0, just to simplify the notation. So here I take the solution of the, well, of the uncontrolled system with phi 1. And since lambda 0 is assumed to be 0, the solution is constant, in fact, for all times. And I want to steer the solution of the first system to phi 1. So I take the difference between the solution of this system for a given U and phi 1. I call it V. Then V satisfies this other problem, still nonlinear. with this extra term. And if I linearize this problem by just dropping this term, I get this other linear system. And that's where the definition of J-null controllability enters. So what I want to do is to, with this transformation, is to steer this initial condition to 0. And the algorithm goes in this way. So I know that I can steer to 0 the linear system with my initial condition by some control p, and I use the same control on the nonlinear system, and I see where I end up. So, So this is the control that steers your system to 0, the linear system. And when you and you also have an estimate on the L2 norm of this control in terms of the initial condition. Then I use this control here, and I estimate the final point I attain at time t, which will not be 0 because this is a nonlinear, this is different. Control that steer this system to 0 will not steer my nonlinear system to 0, but I will be able to estimate this error. And in fact, this error is quadratic with respect to, well, the norm of the initial condition we know. And this quadratic dependence adds up as I repeat this step by step on other intervals, like if I go from capital T to 2t, and so on and so forth. Okay. Now, of course, this will not take me to 0 in finite time because I am repeating on the interval of the same time length, capital T, this procedure. So I get closer and closer because of the quadratic dependence of the error, but I will not touch 0 in finite time. But the thing is, you see, and so on. The thing is, I can implement this strategy on subsequent intervals of in decreasing length, tau n plus 1, and hope to choose my decreasing sequence in such a way that well, the sum converges. In order to do that, so essentially you use the Newton type algorithm on a decreasing sequence of intervals, and if you choose your sequence of intervals of the form a fixed time t over j squared, you can actually make the plan work and obtain at each tau n an estimate of this form that, of course, goes to 0 in finite time because this sum is, well, is capital T times pi squared over 6. And so you reach 0 at this time. Since this capital T was arbitrary, you can control your nonlinear system to 0 at any time. And this means controlling the original system to phi 1. So this is the idea. And the idea relies, of course, on conditions that, well, on this notion of J-null controllability. So let's look at conditions that ensure J-null controllability. And they are essentially of two kinds, one on A and one on B. The condition on A is a sort of gap condition. So we need a uniform gap condition for the square root of the eigenvalues. Now I am subtracting lambda 1 because we allow a finite number of eigenvalues to be negative. So, but this condition means that the difference of the square roots is bounded below by a uniform constant, positive constant, alpha. And then a condition on B, which is sort of a spreading condition. course. You want to be able to steer your system with this action B phi j. So what you don't want is B phi j to be confined in one or in a finite number of directions. And this is what this spreading condition means. Well, in the first place, you want this to be different from 0. And in fact, you want all the others to be different from 0, B phi j, phi k, although you can allow, you must allow some, well, this has to go to 0 as k2 goes to plus infinity, because this is the Fourier coefficient of this vector. But the decay rate has to be controlled below, bounded below in some way. Here I am assuming a sort of polynomial decay rate, lambda k minus lambda j to some power q. So this has to be bounded below by a constant beta divided by this factor. So under these two, I will comment on these assumptions in a minute, but under these two conditions, spreading condition on operator B, so the identity will not do in this context. B taking B equal to the identity will definitely not do, because you will not have this lower bound satisfied. So under these two conditions, the pair AB is J null controllable. Now the J enters here, right? The dependence on J is J null controllable in any time, and you can provide the required estimate on the control cost Nj. Comments. Of course, these are okay. So the nonlinear results, as I explained, relies on this assumption, J null controllability. J null controllability is ensured by this, for example, by this sufficient condition that we have just seen, but it could be ensured in different ways. Comments on these two conditions. The gap condition, well, is quite restrictive. Essentially, the models, the PDE models you can treat are one-dimensional in space, and other similar cases. On the other hand, the control action you allow is very weak because it is bilinear, and also it is represented by a scalar function, right? So in order to have a stronger control action, you should allow your control to depend at least on the state variable. But that is, of course, more difficult to implement. So this is a very weak control action, but easy somehow to implement because it's just function of t that multiplies your coefficient. And this is about the gap condition. Comment on the spreading condition. Again, this is just sufficient. But on the other hand, if we look at the linear system, condition that ensure the J null controllability of the linear system must require some kind of condition of this sort. Otherwise, it would just be impossible. I mean, if you don't have all these Fourier coefficients different from 0, then you will find direction that cannot be steered to 0 by this kind of control action. Okay, now let's look at some examples. So this is the heat equation with a bilinear control on the potential on the 0 order term with Dirichlet boundary conditions on the interval 0, 1. So you can recast in this abstract framework. And your operator A is minus the Laplacian, the second derivative with 0 boundary conditions. And then your operator B is just a multiplicative operator times this coefficient mu of x. Then you compute easily the eigenvalues and the eigenfunctions. And in this case, the assumptions on the eigenvalue. The gap assumption is guaranteed. We are in dimension 1. The eigenvalues are this form, and therefore the gap condition comes for free. Well, and for the spreading condition, well, so your B operator is the multiplication by mu. So you compute these Fourier coefficients. You compute some integration by parts, and you get to this form, some kind of boundary term plus an integral term, distributed term. And you want these scalar products to be different from 0 and bounded below, in fact, by some rate of polynomial type. Now, this term is going to go to 0 as k goes to plus infinity, because it's a Fourier coefficient of this function here. So this term goes to 0 faster than 1 over k cubed. This term goes like 1 over k cubed. Therefore, this is the one that dictates the decay. And if I have that for a finite number of coefficients, the scalar product does not vanish, then I am done, because, and if this boundary term is different from 0, then I have done, because I have a polynomial decay rate. And in fact, here the sufficient condition to have the spreading assumption satisfied are this one and this one, in order to assure that this boundary term does not vanish. And then you get this kind of lower bound, and examples of coefficients mu that have these two properties are polynomials. In fact, something like x squared will do the job. And therefore, you can obtain a local controllability result to the, for example, to the ground state solution. The solution associated with the ground state, if mu is quadratic for an initial condition in a neighborhood. So as you see, I mean, this kind of controllability result selects classes of multiplicative operators, of functions here, such that then for any initial condition, you can find a function p of t that steers the system to 0. Okay, let me go quickly on the extensions, because well, time is going fast, gone by fast. And the first extension is when is to allow B to be unbounded. This will this is required if we want to treat, for example, the Fokker-Planck equation we saw at the beginning. In the unbounded case, essentially we have the same result as in the bounded case. We only require B to be dominated somehow by the square root of A. If B is dominated by the square root of A, then under the same gap condition, under the same spreading condition, I have a local controllability result to the, for example, to the ground state solution, but in fact to any solution, in the topology of this space, which is a stronger topology. With this result, one can treat the Fokker-Planck equation, for example, with Neumann boundary conditions. So partially reflecting boundary conditions. Again, you rewrite the system as an evolution equation. Now you take the Neumann Laplacian, and your operator B is this operator, the derivative of mu times phi. So it is unbounded because of this derivative, but it is dominated by the square root of A. And then again, you want to check all the assumptions. And here again, it is easy to find the eigenvalues and eigenfunctions. The first eigenvalue is 0, in fact, because of Neumann boundary condition. The first eigenfunction is the constant 1. And you can control, in fact, well, provided you choose your coefficient mu in order to have the spreading condition satisfied, which means for a finite number of indices k, this different from 0, and there's this boundary behavior also of mu satisfied. If you have choose mu in this way, you have this lower decay rate, and therefore you can use the abstract result to recover controllability. And an example of coefficient mu, which has these three properties here, is any polynomial, any power, in fact, greater than or equal to 3. So with this kind of powers, you can control to 1, in fact, your the law of your process, the solution of this Fokker-Planck equation, even though, I mean, here you have only partially reflection on the boundary. Okay, well, some concluding remarks. Well, you can extend this, you can deduce from this local controllability result some generalization by extending the decay rate. Instead of taking it polynomial, you can take some exponential, and also you can allow more general behavior of the control cost. And also you can deduce some global exact controllability results from these local ones, typically on, for example, on strips or cones in the Hilbert space. And by that, I mean, you are in this Hilbert space, you fix your first eigenfunction, then you can find a sort of neighborhood on this straight line of radius R1, such that if you fix a strip of width R, capital R, here you can steer your solution starting from this strip to the evolution of the eigensolution in a sufficiently large time. Now, if you take U0 very large, you need more time to go. Okay, but this is this problem is reduced to the local controllability result I explained before. Okay, now let me go to the second part. In fact, I don't have much time, but I'll try to explain it quickly. Here we have, for example, a linear heat equation, which again we try to control with a scalar input, P. But our control is intended to, in this case, to keep the energy level of the solution constant, to preserve the L2 norm of the solution, to keep it the same as the initial condition. This problem was first addressed in a paper by Caffarelli and Lin, Fangua Lin, and solved, in fact. And indeed, you find easily that if a solution exists, it has to have this structure where V stands for H1 here, the domain of the square root of the Laplacian. And so as this non-local behavior with respect to U. So maybe I skip the abstract setup of the problem. The only thing to be aware of is the fact that now to stress the difference with the first kind of results, here I have denoted by A, the Laplacian. So now this A corresponds to minus A in the first part. So A is the dissipative operator, and B, well, B may be nonlinear in general. So our controllability problem boils down to an invariance problem for some kind of nonlinear, quasi-linear evolution equation. And then we can apply to this situation some result ensuring the invariance, for example, of the sphere, like in this problem. Now, there are several ways. There is an enormous literature characterizing invariance of a domain for evolution equations. I will not even try to summarize all the people who contributed to this theory, starting from the original work in finite dimensional mentioned by Nagumo. Here one can use a characterization of invariance of a set K given in this form. A certain set K is invariant if you have an inequality satisfied by the dynamics and by any dynamics and by any proximal normal to your set K, which in the example of Caffarelli and Lin is a sphere in L2. So nu stands for normal to your set K that you want to prove to be invariant. And okay. And in our case, we can apply this result. The condition for invariance is easy to satisfy. And so we get that the unit sphere is invariant for our problem. And using the invariance of the unit sphere of the L2, we can also prove that this kind of equation has a global solution. For that, you need a boundedness result in the norm of H1, in the norm of U. The fact that U as a bounded L2 norm will not be enough, but this boundedness of the stronger norm is easily deduced by a sort of multiplier energy method. You multiply your equation by U prime and you deduce that the norm in V is decreasing and therefore it has a global solution. Concluding remarks on this kind of research direction. The invariance of L2 energy has been studied in different contexts, starting from the work of Caffarelli and Lin, for example, by Mai and Cheng, for this kind of nonlinear equation with this kind of sign on closed means compact manifolds without boundary, and also for Navier-Stokes equation on the 2D torus. By using the L2 energy invariance, one can study the asymptotic behavior of solutions. This has been done in the linear case by Caffarelli and Lin, for this kind of equations by Mai and Cheng, but it is very interesting to do the same analysis when here the nonlinear term has the opposite sign, the bad sign with a plus, or for Navier-Stokes equations on the torus. And this is work in progress that will need a whole new seminar to be described. And so maybe we keep the details for the future, also because the work is just in progress now. So with that, I would like to thank you again for your kindness, for your attention. And I hope I stayed, well, roughly in the time. Thank you.
Thank you very much, Piermarco, for this wonderful talk. So now we're gonna open the turn for questions and comments.
Okay.
If anyone has a question or comment, please open your microphone or type your question in the chat.
Yeah.
Or raise your hand.
Maybe let's keep the screen. Ecco.
Let's wait some Someone, oh no, it was just one. So, Piermarco, I have some questions.
Okay.
One question is about how is the cost for the bilinear controllability? Because you know the cost, no, for the G null controllability, right? And the precisely knowing of this cost, you control get the controllability for the bilinear.
Yeah, and then you can derive a similar bound for the L2 norm of the control for the nonlinear problem. Let me come back here. Okay, we know the cost for the linear case, and then we add up the controls, right? And so your control for the nonlinear system will be the sum of the p's on each interval. And again, you use the control, the estimate on the control cost on the interval to get an estimate on the L2 norm of your P. But you do get a bound, in fact. Yes.
Okay. And also, at which step you use that the initial condition is close to?
Well, essentially, it is here, right?
Here, okay.
Because you get an estimate for your V of this form.
Yes. Okay. Okay. I see.
And
I see.
Whereas I don't know. Okay, so I said that. Let me go to the here maybe. No, on the extensions. Sorry. Let me. To. Okay. Okay. Here. So I said that in fact one could allow more general dependence of the control cost than this, like this one with alpha.
Yes, we should
greater.
Analyze the power of alpha.
But I don't know. All my examples essentially come with this kind of bound on the controllability constant. I don't know, in fact, any significant example where I get a worse behavior like this.
When we have a fractional Laplacian, no? Maybe.
Maybe.
I think that you have some cost like that.
Behavior like this, right?
I think.
So by replacing the second derivative by some fractional, maybe.
Okay.
Okay.
I also, for instance, I don't know if I missed something. You mentioned also some extension to the generate parabolic equation with bilinear control, or
Yes, there is a paper. Yes, on the generate equations. Then, of course, well, I mentioned in the references. In that case, your multiplicative coefficient mu of x has to be related to the degeneracy exponent. So if your coefficient, diffusion coefficient, degenerates like x to some power alpha on 0, 1, then your mu has to be some x to 2 minus alpha. And then you have a similar approach. Of course, the eigenvalues are computed differently. They are related to the Bessel functions. The eigenfunctions are related to Bessel functions. But but the result is the same. You can control to the eigensolutions. Okay,
I have 2 last questions. Then another one is about I mean, okay, your problem is nonlinear because if you see the pair state control is a nonlinear.
Yeah, you could also consider a nonlinear operator B and make it even more nonlinear.
No, you can. For instance, the case of Burger's equation. Is it possible to get some controllability for Burgers with this kind of bilinear control?
You mean the viscous Burgers equation?
The viscous Burgers, yes. You have the nonlinearity is y, yx, and also you have the nonlinearity of the control, no? The bilinear control.
So you put bilinear control.
You put a bilinear control in a nonlinear system. Yes.
Well, here the operator B has to be linear. In the paper by Bochard and Marbach, that was restricted to the 1D heat equation. The operator was allowed to be nonlinear, but just on the 0 order function. So not on the UX term, on the gradient. So
here
my
maybe
answer is I don't know. I mean, it could be. I mean, here operator B in this talk is assumed to be linear, although unbounded.
Yeah, maybe the step, no, the step that you apply the Newton method, no. Maybe you should.
No, I really need for this the linearity. The extension would not be just immediate.
Yeah, maybe from the J nu controllability, you should go to the nonlinear with a linear control, no, and then you apply the Newton method, no, as you maybe if the okay.
Yeah, but then you will have to give conditions in order to have the genuine controllability for the nonlinear case. I don't say it is hopeless. I'm just saying that it will require some work if possible.
And the last comment and question is the example that you have in mind, all then are in 1D, right? Because the control is just time dependent.
Yeah, 1D or like higher dimension, but with symmetry, that with radial symmetry. Yeah.
Okay, thank you for.
On the other hand, you can have like networks, some kind of graphs. Yes, but still they are in one. They have a 1D topology. Yes, yeah, but it may go to graphs. Okay, thank you.
Okay, so there is another question or comment? If not, let us thanks again, Piermarco, for your wonderful talk. And now I give the word to Sandra.